All right, here's what we got going on today. Today, we're going to be talking about power. First, we're going to talk about the bell work. Bell work is review bell work. So number one, a 0.5 kilogram ball is dropped from a third-story window, which is 20 meters above the sidewalk. What is the speed of the ball just before it strikes the sidewalk? What do we have? We're given a mass and a distance, so I do like that we're given a mass of 50 kilograms and a distance of 20 meters. But what principle are we going to use in order to find the speed? Gravity. Gravity is an acceleration. So how are we going to use gravity?
MGH.
What's MGH?
That's potential.
That's potential. So we can find potential energy easily, correct?
Which is equal to kinetic.
Which is equal. Is it equal to kinetic?
The initial and the final are going to be equal of them added together.
What was that again?
UG initial and kinetic
Good.
will be the same as the final.
So what Gage said is we can use the conservation of energy principle. By using the conservation of energy principle, woohoo! This might work. Conservation of energy says kinetic plus potential gravitational is equal to the kinetic plus gravitational, where this is all initial, is all equal to final. This makes sense?
Yeah.
Good. So, what is the kinetic energy at the very beginning?
Roughly 100.
Roughly 100. Why is the kinetic energy at the very beginning roughly 100?
No, not the kinetic. The potential is roughly 100.
The potential is roughly 100. How did you find that?
Mass time.
MGH. There you go, Tyler. So MGH is, what about kinetic? What's the kinetic at the very beginning?
Zero.
Zero. How do you know?
Because it's at a resting.
It's at a rest. Is the object moving? No. So kinetic at the very beginning is zero. Let's look at potential at the end.
Zero.
Why is it zero at the end?
It's a 0 point.
It's at a 0 point. You know, it hits the sidewalk. Usually we say the ground is a 0 point, correct? So no potential at the end. So this tells me, Gage, you was right, that the initial potential is going to be turned into kinetic energy. Now, if energy changed, this is a bonus question. What was doing work? Work is a transfer of energy, correct? What was doing work? Gravity. Gravity was doing work. Good job. So, let's go ahead and solve this. The masses cancel because it's the same mass. Multiply both sides by 2. So 2 times gravity times height is equal to v squared. Take the square root. And when we do that, what answer do we get? 2 times 10 is 20. 20 times the height of is what? 400. Square root of 400 is? Answer is? D. 20 meters per second. Conservation of energy. This is a review before Thanksgiving. Let's look at the second one. A crane can lift a 500 kilogram mass to a height of 30 meters in 2 minutes. The work done by the crane is?
It's force times distance, but you got to solve the force.
All right, Gage, good. Everybody in agreement? What about you, Hunter? You like it? So what's work? Force times distance. So work, force times distance. What extra information are we given that we don't need? Time. Time doesn't matter what time it is.
If we were solving for power, it would.
Good. If we're solving for power like yesterday's lab it is. So, what is the force?
500 times 10, so 5,000.
500 kilograms times 10 meters per second squared. That gives me my weight. And the distance is 30 meters, correct?
Yeah.
500 times 10 is 5,000. 5,000 times 30 is 150,000. The correct answer is E. I'm liking it. I'm liking it. I'm liking it. Let's do something. Yeah, I need to fix it. D. Control copy. Control paste. So D and E. All right, make sense? Good. On the way in, did everybody pick up a power sheet? All right. Everybody on this side pick up one? Here's a couple. Pass it around. Did everybody, if y'all didn't pick up one, pass it down to the end, please.
Mr. Williams. I don't remember. Mr. Williams. Mr. Roberts. Mr. Roberts. I'm thinking Roberts. I don't know about Roberts. He was the one who.
No, I know. My dad just doesn't know. No, because my sister
All right, so yesterday, what did we do yesterday?
Lab.
Huh? What? So talk to me about the lab.
We learned about power and running up steps and measured steps and multiplying steps and
1 pound thruster, 1.4.
Whoever weighs the most, does the most work.
There you go, I like that. Whoever weighs the most does the most work. What do they do the most work against?
Gravity.
Most work against gravity, good. So anyways, so whoever they had the most mass, so mass times gravity, as long as they move, as long everybody went to the same height, which was 5 meters yesterday, so whoever had the most mass does the most work against gravity. What about power? Who had the most power?
Alan.
Why did Alan have the most power?
More weight. More weight, but he's still ran.
He weighed more than most, but he wasn't slow whenever he ran. He got up them steps in a hurry. So today I would like to do a little bit on power. All right, and with power, you're going to help me fill some stuff out. So anyways, notes. What is power? That wasn't a question, that was a statement.
What is the unit of power?
What is power?
Correct.
Correct, there you go. W-A-T-T, what is power? So anyways, what the definition of power is? Power is the
Rate of doing work.
good, I like that. Rate of doing work. Power is measured in which is a joule per second. Because when we think of rate, I want you to think of slope. Remember, whenever we talked about rate, when we was doing kinematics, the rate at which you travel is called your speed. So the slope of a distance time graph is speed, and the rate at which your velocity changes is your, remember, acceleration. And notice that the slope of a velocity time graph was acceleration. So power is the rate at which work is done. So it's the slope of what type of graph? You're close.
Work per second.
There you go. There you go. Good. I wish I had a piece of candy or something because I'd give it to you on that.
guys start?
No, he had those out the other night.
So notice just because power's a joule per second, which is joule is rise, you're gonna put that on your y-axis. Second is time. Second time, which is your run, rise over run. So it's a joule per second. We know it's joule is energy, right? Energy or work. So you're talking about work per time. So the slope, power. The slope is power. Isn't it? So I like that. So anyways, this simply means power is work divided by time, or a change in energy divided by time. Notice I also said, what can work be? Work is a change in energy. Mainly a change in, we talked about it, a change in kinetic energy. And we called that the work energy theorem. Remember that? The change in kinetic energy is work. Also the change in potential energy is work too, because with a pin falling or a ball dropping, notice gravity is doing the work. Alright, so let's look at an example right here. Lover's Leap is a 122 meter vertical climb. The record time is 4 minutes and 25 seconds. Achieved by Don Osmond, who was 65 kilograms. What was his average power output during the climb? So since power is work divided by time, which is equal to a change in energy over time, what was his energy change? Well, what is his work? Okay, let's talk about that way. How are we going to find work? 65 times 10 times. Good job. So his work is the same as its potential energy to get there, correct? Good. So I'm going to say mgh over time, which is 65 kilograms times 10 meters per second squared times 122 meters over.
But why are you using potential energy?
The work required to lift an object up to a certain height. The work that I take to lift it up, the object gains potential energy. Notice, what's mg? That's a force, right? What's h? A distance. Force times distance. Notice energy and work are very related
So
because
potential energy is work.
potential energy can be work.
Can be or is.
It can be. It's not looked at as the same thing it's work, but it can be work. I do work on this pen to lift it up. Because I do work on this pen to lift it up, the pen gains potential energy. How much potential energy does it gain? It gains the same amount of joules it took me to lift it up this high. So if it took 10 joules of work to lift it up, the pen gained 10 joules of potential energy. So they're not the same, but they're very related. All right, time. Kobe, what about time?
What we converted to
4 minutes and 25 seconds.
All right. 4 minutes, 25 seconds. So 60 times 4, which is 265 seconds. Let's look at it. 265. So by putting this in the calculator, what do I come up with his average power output? How much?
300 watts.
300 watts, 299, 300. What are we going to say? 300 watts?
Our biggest
299.
yesterday was 101, so doing pretty good.
Okay, let's say 300 watts. So it took 300 watts. This must have been a little guy. Notice he's only 650 newtons. Is that a little guy or a big guy?
For pounds, we divide that by. No, 1 pound equals 4.4 newtons. So divide that. How many newtons is he?
65 times 10 is 650 newtons, divided by 4.4.
It weighs 147.
He weighs 147 pounds. Is he a big guy or a little guy?
Pretty small guy.
So he has to travel real fast in order to.
Depends who you are. Like Brennan, I'm 5'7"
All right, so that's the first one. Second one. A car accelerates from rest to a velocity of 15 meters per second in 4 seconds. Calculate the power output of the car. Same here. Power is a change in energy over time. His change in energy is going to be his kinetic energy, which is going to be 1/2 mv squared over time. So, what is, let's see, half of 1,000, 1, 2, 3, and 15 meters per second squared over 4 seconds. So this should give us roughly,
Is that MV squared?
yeah, 1/2 mv squared.
28.
Roughly 28,000 watts,
I know.
roughly,
Yeah.
28,125.
roughly. All right. So far I've talked to you about power. When we did the lab, we talked about power. We talked about work divided by time. We looked at it as work can also be called, which is force times distance. We also looked at it as a change in energy, because work can be a change of energy over time. I want to look at work, I want to look at power one last way.
They were at lunch and I
All right, check this out.
Hey, Franklin.
Change in kinetic energy.
Is that what change of energy is?
Change in energy is, I used it as a change in kinetic energy, final kinetic energy minus initial. Notice it accelerates from rest, so the initial kinetic energy was 0. Final kinetic energy, he had a velocity. All right, so check this out. You ready? I told you that power, what did I say power was?
Change in energy over time.
Change in energy over time. What also is power? Work over time. And what is work? We know work is force times distance, right? So force times distance over time, right? Everybody agree that this is power?
Yes.
Okay, I want to show you something. What's distance divided by time? Speed or velocity, correct? Distance over time is the rate at which.
So speed times force is power.
So check this out. Since distance over time is velocity, power can also be force times velocity.
That's the next little one?
That's the next little box. Since power is equal to work over time, and force times distance over time is work, force times distance is work over time, because of this right here, force times the velocity is power. Let's look at it. A student uses 120 newtons to push a block up a ramp at a constant velocity of 2.2 meters per second. What is their power output? 140 newtons times a constant 2.2 meters per second.
300 watts.
300 watts?
8.
308. Now, here's something to remember. This formula is only useful when velocity is constant. If velocity is not constant, guess what? Formula is not useful at all.
Could you use it still find like instantaneous power?
You never need to know instantaneous. I won't tell you that in here. You know what I mean? You won't have to do that. Technically, you could. So here's what I got for you. You ready? What time we out of here? All right. It's 1:35. The remainder of the time, you have 4 problems to do. Here's what's due tonight. You got 4 problems in which I want you to talk about. If you need to do it in groups, talk about it, okay? The lab itself. I haven't got online so you to turn the lab in. Do we want to turn the lab in online or would you rather do it with paper?
Paper. I'd rather just hand it to you right now.
All right, so here's what we'll do. In the tray, you turn the lab in the tray on the table here and make sure you do terms. Remember we did terms and that you had to write. Procedure, because you had to rewrite the procedure, or at least write a procedure that can be reproducible. We had pretty much everything else. Calculations. Remember you had to do the chart so that you had to do the calculations of ranking the work and ranking the power. And then once you have that, turn it in. If you got any questions, get with me.
Can we do that, or can we turn that tomorrow?
Yeah, if you need to rewrite it, turn it in tomorrow, turn it in tomorrow.